All right, welcome everybody to a brand new semester of IS50V, second semester computer science. In IS50A, we talk more about how to use Unreal Engine and things like that. And this semester, we're going to be talking more about how engines work. We're going to be doing some stuff with Unreal Engine, and we're also going to be writing code to sort of understand the basics of a graphics engine itself. Because the more you understand about how graphics engines work, you can either write one yourself, or you do better when you're using a graphics engine because you're working with it instead of against it. So the first thing we're going to talk about today is how a triangle gets up on the screen. So the basics of every 3D engine these days, for almost all of them, voxels are a little bit different, but the notion is you've got these models, like let's say my hand is a 3D model, and it's made up of thousands or millions of triangles. And then those triangles need to get drawn on the screen. And the process of taking a triangle in 3D space somewhere and ending up with pixels on the screen, you can broadly call that rasterization, where you end up having a grid of pixels. That's your screen buffer, is what we call it. And at some point, the screen buffer gets filled with colors representing what you're seeing inside of the world. And so there's all sorts of tricks, like this is anti-aliasing here, to make these things look good. But the basic way the process works is you've got a camera that's in a 3D world. There's all these 3D models out there. The camera has what's called a camera projection, and it's in space looking in a certain direction. This is represented with matrix math that we'll get into at a later date. And then you've got all these 3D objects that are in the world. Some of them are in front of the camera, some of them are behind the camera, some are to the right or left of the camera. And you do a lot of optimization techniques to clip these things away. In other words, if something's behind the camera, don't draw it. If something's off to the right side of the screen and it's outside of our field of view, don't draw it. If something is on the edge of our field of view, we clip it and we draw just the half of the triangle that's visible. At the end of the day, all these things get projected into what's called screen space coordinates. Typically, the top left part of your screen is considered 0, 0, but other systems exist. Sometimes the center of your screen is 0, 0. The right is 1, 0. The left is -1, 0. It doesn't really matter at this point. We're doing a really fast, high-level overview of it. But somehow, some way, a triangle is going to be mapped to this point, this point, and this point on the screen. And then it's going to fill the triangle. So basically, you've got these 3 points on the screen somehow, and they're going to be filled in with, if you're doing flat shading, just let's say you're drawing a red triangle, everything's red. And it just puts red pixels in on every row that is inside of that triangle. And then you're done. But in most cases, you're going to be grabbing textures, you're going to be grabbing normal map data, you're going to be getting lighting, and all these things. There's a lot of math that goes on to put a pixel on the screen at that point on the triangle, and then you repeat for the next triangle. And if that triangle is in front of the other triangle, like for my eye, right, I'm seeing this hand and not this hand, right? Because this hand is occluding this hand. And so you constantly draw triangles, and if they're in front of the other one, it overdraws it. And if it's behind it, it doesn't get drawn, right? It's called Z-buffering. And there's obviously ways of optimizing that so that if you're inside of a room and you can't see out of it, to not try and draw all those triangles outside of the room, because you're just going to overdraw them anyway. So there's a huge number of steps that take place in the rasterization process that goes from having some sort of data structure in your game engine to ending up with a frame of pixels on the screen. Once that frame of pixels on the screen is ready, it gets shipped off to the monitor. Nowadays, most monitors use G-Sync or FreeSync, which means the monitor is waiting on the graphics card. And when the graphics card's like, hey, this frame is ready to be drawn, it sort of pokes the monitor and sends the frame, and then your monitor updates and shows the new frame. It's like when I'm moving my hand like this, the monitor is updating 60 times a second, 100 times a second, 144 times a second. Whatever the refresh rate is on my monitor, and you get whatever is the lower frame rate of your monitor and what your graphics card can produce. So whichever one's lower, if your graphics card is updating 20 times a second, and your monitor can do 300, you get 20. If your graphics card is doing 300 a second and your monitor updates 60, you get 60. So older monitors just update at a flat refresh rate of like 60 is very common, and so when you have an older monitor, not too common these days, especially for gamers, but you'll still see them. What happens? The monitor asks the graphics card, "Hey, what kind of thing should I be showing right now?" And it just grabs whatever's ready. And so, like, let's say you're like a fraction of a second before the latest update, it's going to draw the old data again. And so, if your game is running at like 59 frames a second, it takes slightly longer than a 60th of a second. So the monitor is going to come in and grab the same frame twice, and you're going to effectively get 30 frames a second out of a game instead of 59, which is why we use G-Sync and FreeSync. You can actually get frame rates other than 60, 30, 15, and bad. So that is sort of the high level thing. There are these things called shaders that come into play. There's vertex shaders, geometry shaders, and fragment shaders. They call it a pixel shader here, which is kind of the it's still used like that term, pixel shader. Fragment shader is the more technically correct phrase these days. What is a fragment? Most of the time it's a pixel. So that's why people still call it a pixel shader. It is like this box that we're drawing on the screen and figuring out what color it should be. However, fragments don't have to be pixels. So for example, if you're doing like some sort of like fancy anti-aliasing, you might actually up the resolution of your screen by four times more than you can actually draw on your monitor, and then average the results together to get anti-aliasing. Anti-aliasing is when you guys know anti-aliasing? Boss? Yeah. Smoothing the lines out. So let's see, good example here. Yeah, so you can see all the jaggies right here. So you can zoom in on it. So you see how like all these lines are being drawn with like jagged edges. When you anti-alias them, it smooths them out. So you get, and the reason for that is because pixels are squares, right? And so if you try drawing like a diagonal line, you get a stair-step pattern, which your eye can see if the resolution is low enough. And so some people will anti-alias by simply drawing 4 times as many pixels and then averaging them. It's not a very good way of doing anti-aliasing. I mean, it's good, but it's slow, so it's not a good way. So the point is that like a fragment isn't necessarily a pixel, and a pixel isn't necessarily a fragment. You can go the other way. You can actually like DLSS. Have you guys heard of DLSS? Deep Learning SS. Deep Learning Super Sampling. So what this does is it's an NVIDIA thing. I think AMD has its own equivalent of it, whose name I can't remember off the top of my head. But essentially, what you can think of it as is this is like maybe at 4K resolution on a 4K monitor, and then with DLSS on, it actually renders everything in 1080p, which is a quarter of the pixels. So you get a much higher frame rate when you do this. But you're like, oh, but aren't you just running it at 1080p? Like, isn't that bad? You're losing image quality. Well, what it does is it uses like a neural net, essentially. And it has to be trained on the specific game. So you can't just use DLSS on any game. It has to have been trained on your game. And so basically what it does is it says, it sort of dynamically upscales it from 1080p to 4K. So your monitor thinks it's getting a 4K signal, but the game's only being rendered in 1080p, but it uses what kind of graphics it's been trained on to sort of upscale the graphics. And if you look at this, it's actually not too bad. Like it's not full quality of like a full 4K. Here's the full quality. We go over it here. See, it's a little bit more blurry, maybe. I don't know. Yeah, like that part there looks a little bit worse. Like that brick with the crack in it right there. It looks a little bit worse. It's like pretty good. Like, I mean, honestly, like from a distance, like it's pretty good, and it gives you the FIPS. You know, it gives you the FIPS you need, the frame rate. So it's supposed to help lower end cards hit higher frames. No. I mean, you can use it for lower end cards, but like Cyberpunk, if you have Cyberpunk and ultra settings, DLSS like doubles your frame rate. Like it. So even on my 4090, like it actually makes a huge difference. And the quality, like I said, you'll see. You know, if you like zoom in and you like look at it, it's like, you can see these cracks up here and over here. They're like kind of blurred out. Like you can like tell, but like you can't really tell. You know what I mean? Like it's like from a distance, like it looks pretty good. You know, like I don't know, like without zooming in. Looks pretty good to me. So again, the point of that is that its fragments are not pixels, right? So it's the fragment that it's rendering is actually like 4 pixels wide, or 2 by 2, and then it gets upsampled into 4K resolution. So what is a shader? A shader is a program, and it is a program that will run on your graphics card. Essentially, your graphics card is a absolute beast of a computational engine, assuming you have a graphics card. Shaders are black magic. Not really. I mean, you've done materials before in Unreal Engine, and a material in Unreal Engine is a shader. So you've programmed shaders before. You've just done so in a graphical fashion, where you're like connecting nodes together. If you look at the bottom, it'll actually tell you like how many instructions your material is. And let's see if I can launch fall 2023 up here. I'll let that launch in the background while I'm talking about this. And so there's a couple different kinds of shaders. So a pixel shader or a fragment shader is the most common one that we talk about. Essentially, you say, hey, what color should be drawn at this point? And that shader is going to do things like grab the texture. A texture is a picture. Grab the texture that you have mapped to the side of the wall. So for example, if you have it, I can just apply this really gross texture here. Oh, it's transparent. That's kind of cool, actually. I was gonna say it's gonna look terrible, but that's pretty dope. I don't know what to say. All right, here, let's try this one maybe. Okay, that looks garbage. All right, and so a texture is literally just a picture that you're putting on the side of the building. That's honestly kind of cool. It's like a modern art installation now. And so it's just a picture. A material does things like concrete tiles here. It does things like having normal maps. You can see like this crack here is picking up light from the sun and shadowed from underneath. So if I were to drag out like a point light here, you can see that's not just like hard-coded. As I move the lights around, you can see that the light on the crack in the concrete is behaving realistically. And so there is a pixel shader in there that is going to be, there's the normal map basically on it, that is going to be reacting to the light based on the direction of the light and the direction that the normal map says is up. A normal map is basically what is perpendicular to your surface. So the normal map allows you to simulate cracks and things like that without actually having any geometry. If I slow down my camera speed a little bit here, zip that down. You see how this thing is actually perfectly flat. Like there's no actual depth to anything here. It's just simulating it. It looks like there's a crack. That's kind of like, it looks like there's a groove in the surface there, but it's actually simulating it. It's simulating it using a normal map. And so basically the shader is saying, hey, what angle is the light coming in at? What is the simulated normal? Like in the crack, it might be like this. On the rest of it, it might be like this. And then it computes the lighting based on that. And it looks pretty good. And you don't have to use a lot of geometry for it. So if we go into wireframe mode here, you can see that the wall here is just a couple triangles. Like, it's not a lot. It's maybe a few more than you think, but it's like 1, 2, 4. It's like 4 sections, each one made of like 4 triangles. So it's like 16 triangles we're looking at here. And it looks pretty good for something with 16 triangles. Like all these like little dips and dots and bips and bops on the right? It's like parts of it are lit better than others. All of that is being computed by the shader. Yeah, a bump map is another name for a normal map. Yeah, a bump. So sort of. So a bump map technically holds the elevation of every point on the surface. So bump map would hold, like, we're at negative elevation right here. It's essentially the integral of the normal map. Am I doing that right? Normal map. Normal map is the derivative of the bump map. So they're essentially the same thing, but they're technically they're mathematically equivalent to each other just by taking the derivative, the partial derivative in every direction of the bump map will give you the normal map. So yeah, it's the matrix, right? So it's the same but different. I don't really care. Okay, you might hear me call it a bump map occasionally, but it's a normal map that we got here. So pretty cool stuff though, right? And so let's take a look at the shader for that. So if we open up the material for the concrete tile material there, let's see. Window stats. Okay, right here. So the base path shader, 273 instructions. Vortex shader, 262 instructions. Texture samplers, 9 out of 16. Texture lookups, shader count. So there's 4 shaders actually involved in this thing. If I delete some things, maybe delete some things, and apply it. See if that changed anything. No, not really. All right. Maybe it's because I have to actually delete the nodes. No. Let's close you and not save it. Let's just make a new material. So come in here, new material, named Bob Matt. Save. And let's just like make the world's simplest shader, right? So you thought these were materials, but they're actually shaders. Just look that up. Be like, you're orange. Congratulations. All right. And then let's put this on. Oh, I set my camera speed. And let's make you orange. Okay. There you go. Very complicated shader, right? But there's actually still some stuff going on here, right? Like it's actually, you can see, right? See what's going on here? Like the upper part is getting more sunlight, you know? And then if we have a point light over here, you can see it's responding to the point light, right? So there's still some stuff going on here, right? So if we open you up, you can see this one is 224 instructions and 256 here. And so there's still actually a lot of stuff happening because even though our material itself isn't very complicated, it still is reacting, it still has a normal map. It's just a normal map that's always pointing out from the surface. It's handling lighting, it's actually doing stuff more than what it appears to right here. But if you want to know what your 20 shader, that's amazing. Okay. If you want to know like roughly what the cost is of your materials, this is sort of like a, first pass look at, what the cost is going to be. Because it basically means that your GPU is running 281 instructions to get the color on the screen. So you do glass, and glass is doing a lot of stuff, right? Like it's got the reflection and refraction on there. doing a lot of stuff, but even still, the instruction count's not too bad. So those are shaders. And for your homework assignment for today, you guys will write your own shader from scratch. I like this. I mean, it's ugly, but like, it's like kind of cool. I don't know. Yeah, that looks terrible. What did I have earlier? Bricks here. I mean, that is kind of neat. Let's be honest. I think I'm just gonna leave that. It's like this modern art installation or something. You are gonna write your own shader, yes. So let me show you what you're gonna do for that. Let's see if there's anything else here that we want to talk about. Yeah. So vertex shaders and geometry shaders actually move the geometry around. It's like if you want to have waves, you can actually have the surfaces moving. Whereas what we were doing with the pixel shaders here, you can see when you look at it from the side, it's perfectly flat. None of those vertices are actually moving out or in for the cracks. It is just how it gets drawn. It's just drawing as if it had a crack on it. It doesn't actually have a crack. With these shaders, you can actually have your 3D models move, which is kind of cool. We're going to be working on a pixel shader though today. So, and this whole semester, you're going to be learning basically how does the game engine get from, a data structure of just like everything in the world to drawing these nice, beautiful things on screen. And there's a lot of steps to that process. And we're going to be kind of going through that this semester. So let's do pixel shaders. Over here, there is a wonderful website called Shader Toy. Building the entire UE5 from scratch, final project. Well, maybe not UE5, but like one of the things that I'd like to do again. The final project we did 2 years ago, I think. We built this in one class session, which was essentially a Doom client. So you can look around. This is like basically Castle Wolfenstein. You can look to the left. I can strafe right. You can see there's like a wall kind of coming at me. The perspective isn't quite right because this is all in text mode. This is actually just drawing spaces on the screen. We have non-square pixels, which kind of makes everything look a little bit weird. But yeah, you might look around. It's lit, kind of. Scroll around here. It's just a text file that holds the map. Walk forward. That kind of stuff. So that was 2 hours of effort. I kind of want to redo that at the end of the semester in this class. Yeah, raycasting. So it basically we can talk more about how that works, but it would be fun, I think, to put together a little like Wolfenstein era engine because it's not actually that hard to do. Like I said, that was 2 hours of work. It's about 194 lines of code. So there's the map. Like that was the corridor that I walked in at the end. That was the wall you saw coming at me. Yeah. 4.5 pages of text. Not too bad. Okay, so anyhow, Shader Toy. So Shader Toy will kind of inspire you, I think. Like, I'm not expecting you to make things like this, which is wild. They just have some incredible shaders on here. This is really cool. We're going to be doing something a little bit more simple. Okay. We're going to do ray tracing now. I'm kidding. It's pretty amazing though. And so let's pause that. It's going to be distracting. Okay. So here is the actual source code to the shader. And the shader is written in its own programming language. It's similar to C, but it's got some built-in classes that are suitable for image processing. Let's put it that way. You must do God rays, exactly. Okay, so here's how the shader you write is going to work. you're going to write a function called main image, and it's going to take in a fragment coordinate, and it's a vector 2. So in shader language, there are vector 2s and vector 3s. They're basic type, a built-in type that have an x and a y as part of them. A vector 3 has an x, a y, and a z. It also has an r, a g, and a b. And the r is the same as x, and the g is the same as y, and the b is the same as z. You can call it either x, y, z, or RGB, or ABC, I think. And they're all exactly the same subvariable. It's kind of an interesting quirk. But it's just a built-in type. And so what it's going to pass in is the pixel location, the fragment location. And so it's going to be like, counting from 0, 0 in the top right, we are 500 pixels over, 200 pixels down. And that is the input. And what you output is an RGBA of what color should be drawn there. Okay, so you take in a screen location and you return a color. RGBA, red, green, blue, and alpha. Alpha is transparent. Typically, that's just going to be 1. Right? So what we see here, if you want to look at if we can run through this a little bit, we're making a vector 2 variable. A vector 2 variable again has two sub. It's a struct, right? So we've made a vector 2 named q, and it's got two subvariables, q.x and q.y. And the cool thing about the shader language is you can actually operate on two of the subvariables at the same time, which is really cool. Instead of having to do, like, if you wanted to divide both of them by 10, like normally in C++ or C, you'd have to say like q.x is equal to q.x divided by 10, right? And then you'd also have to say q.y is equal to q.y, or if you want to be fancy, divided by 10. You guys with me? Like if you wanted to divide both x and y by 10, you'd have to do that. But in shader language, you can actually do both of them at the same time. And so here it is dividing fragchord.x and fragchord.y by the resolution of the screen, x and y. And so this is essentially doing q.x is equal to q.x divided by resolution.x and q.y divided by resolution.y. And it's actually doing two of them at the same time. It's kind of cool. Yeah, it's neat. Like, I kind of wish structs in C++ could work that way. And it also works with vector 3s as well. And so you can do things like multiply it by 10. Let's see if we have any examples in here. Whenever we get to it, I'll show you. There's some cool little shortcuts like that work. So let's say that so iResolution is a global, okay, and we can view the globals up here. And so these are the globals that are passed in and are available to every shader. So the resolution is the number of pixels in the screen. So like let's say that we have 800 by 600 resolution, and we're currently operating on pixel 400 across, 300 down. This is going to set Q. This is going to set Q to be, so we're halfway across, halfway down. It's going to set Q to be, Q.x is going to be 0.5, Q.y is going to be 0.5. Okay. You guys with me? So it's sort of normalizing from pixels into 0 to 1. How far are we across the screen? How far are we down the screen? Yeah, you could do that. It is then going to switch it to a universal normalized coordinate system right here. So what this is doing, so like let's say that we're halfway across, halfway down. So Q is equal to 0.5, 0.5. We're multiplying 0.5 by 2, which is going to give us 1. We're subtracting 1, which is going to give us 0. So the center part of the screen is 0, 0. So this is a very standard coordinate system that almost everybody uses, where the center of the screen is 0, 0. The right side of the screen is 1, 0. Left side of the screen is -1, 0. Bottom of the screen is 0, 1. Top of the screen is 0, -1. And so you can refer to any point on the screen using uniform normalized coordinates that goes from -1 to +1, -1 to +1. And then it is going to multiply the x by, oh, that's the aspect ratio, right? So it's dividing the width by the height, and it's going to multiply the x value by that so that it will handle non-square screens nicely. Time is another input, and so you can see, like, when you run it, I'm not touching the thing. It's actually animating this cool ray traced thing for us in real time. What's happening here is that the time parameter here is being passed in, and then it is multiplying by, it's adding 15, multiplying by 0.45. Probably if we wanted to speed up, we could probably do something like that. And run it, and it's probably running faster now, right? I sped up time. The rotation. Okay, so it's gonna. So you see how the camera is like rotating around the thing right now. So it's taking the cosine of time and the sine of time, and basically it's spinning around that center point. The mouse is another global, and so you can click and drag, and you can see it's getting the mouse location. And based on the mouse location, it is rotating the camera. If I'm not clicking, then it just uses the default one. And so it's just rotating the camera based on the mouse location. And once it has figured out the cameras up and all these other vectors of like what direction the camera is looking, then it goes into the actual meat of the function, which is called ray trace. And so it's going to ray trace from the starting point to the ending point. I believe. And then it's going to do ray trace ray, so it's going to shoot a ray out right up here. And it's basically doing all these like complicated maths, which I could explain to you, except I can't. So let's see if we can find a simpler one. Okay, this one's pretty simple. This is a pretty simple shader here. All right. It's just blurring the screen. Yeah. Interesting. What do we got here? The variable names make it hard to follow. Yeah, everything is named as RO, RD. This is why in like C-Sci 4 they tell you guys, name the things like something meaningful. Yeah, well, the picture, I think the picture is just, probably switch this out. channel 0, okay, sorry. Probably switch it out, yeah. So it's actually not, blurring. Break it. I don't know what happened here. Yeah, so what's happening here? It's grabbing from channel 0. So you're probably going to use this during your thing. You can basically load up a texture, and then you can grab parts of the texture out, and it is grabbing the coordinate. I don't know how that's blurring. What is happening here? So what's happening here is that is the fragment coordinate, and then it's the texture function is what allows you to grab things out of the textures you have loaded up here, and so it's grabbing the it is grabbing the points above, below, left, right, kind of in every direction, and then averaging them together. So it's adding all the neighbors around in kind of a radius, and then it is blurring them together, and then returning that as the color. So if I were to just switch all this out with black, right? Right. If we switch this out with vec3 equals texture. So that's going to grab from the texture sample that we have loaded up down here. We're going to grab from iChannel 0 from the UV, that's our location. Let's see, it's UV divided by the resolution. Okay, all right. UV by resolution by X, Y, Z. Let's try that. So there's syntax error. Right. Let's make the variable name in there. There we go. I left off the variable name. Okay. So you see what's happening here is it is just displaying this is the texture. Okay. Don't you need a variable name? Yeah. Thanks. Yeah. So it's just displaying the texture. It's not blurring it at all. And so that's how you grab pixels out of a texture. And then if you want to blur it, you can just grab people up, down, left, right, add them together, average them, you get a nice little blur out of it. Getting back to that. Leave it out, redefinition, yes. Now it's blurry. Mix, blur, texture. So it's mixing in another texture here. Oh, interesting. I don't know what texture this one is. So it's grabbing smooth stuff based on time. Interesting. Oh, I see. Yeah. So smooth stuff is what is called a why am I blanking on it? Sigmoid. It's related to the sigmoid function. And so these are very useful when you're blending things together. So you can, like if you're having movement of things, they move quickly in the middle, but like when the door is about to shut, it like kind of slows down a little bit. When it opens a little slowly, then it goes quickly, then it slows down and stops. So the smooth step function looks a lot like that. And it allows, it's a form of interpolation. So instead of doing a linear interpolation where, you know, you have this mechanical open, shut, like it'll speed up and then slow down at the end, and speed up and slow down at the end. Smooth step is very, very commonly used in video games. So this is using the sign of the time to choose whether it's doing the original or the other texture, and it's going to go back and forth using the time, which is kind of cool. Let's see what's in iChannel 1. It's this guy. Okay. So that's iChannel 1. That's the texture they have loaded in iChannel 1. And then this is the guy in iChannel 0, which is already blurred, it looks like. So what's happening with this overall thing here is that they've got one texture that's already blurred, pre-blurred for you. and then one that's not, and then that's why it's going from clear to blurred to clear to blurred. They're kind of hacking it with these animated textures already in there, and the smooth stuff. You can see how it smoothly goes from being blurred to clear and back. It's nice, right? It's very nice. We're learning good things in this class. So the shader toy tutorial. They are cheating. So there's a tutorial that let's see, is that one? That actually has good documentation on it. Let's see here. Well, it's in your assignment anyway, but it's going to kind of run you through the process of making a shader on Shader Toy. You guys have till Thursday of next week. There's going to be no class on Tuesday. So I would like for you guys to do two things instead of one thing. The first thing is just to follow the tutorial and link that to me. And the second thing I want you to do is to do something like impressive. Now, the nice thing about Shader Toy is that all of these impressive shaders here exist already, and you can just mess with them, right? And so if you're using somebody else's shader, obviously you have to cite them, say this is from here, and then you're going to have to describe to me, I started with this, and I made it look like this. And you will be judged based on your individual contribution on top of the starting shader. You're not going to be judged, oh, look, you copied and pasted a great shader. No. If you start with an amazing shader like this, whatever changes you make to it, that's what you're going to be graded on. And so just make it look cool. You know, the changes don't even have to be like necessarily a lot of lines of code. You could probably like honestly, if you wanted to, you could probably just go in there and just start changing numbers around and just seeing if you get some lovely accidents. You know, like that's how Bethesda codes, right? You just introduce a bug and keep it. So yeah, that bug looks cool. Let's go with that. Some of the shaders that I've written in the past worked like that. I was trying to do some completely other effect. I'm like, oh, I just made an explosion that looks really cool. I'm gonna keep that. Now I'm gonna go back to my other thing, but I'm gonna keep that one. That one's really cool. So, do you guys understand? So you're gonna run through the tutorial, and you are going to do a tutorial level shader where it displays a texture, and maybe you click and drag and it tints the thing differently. I can kind of show you what that would look like here. It's like this would be what I kind of expected you guys from for the first part of it. So I can run you through this shader as well. So it's just got a texture loaded up, these rocks or whatever. The input parameter, that's what the in stands for. It's an input parameter. The input parameter is, again, the pixel location on the screen. You then normalize. I did it in 2 steps instead of 1, kind of just to show you guys how that looks. But you could do these together. You could just say what is it, xy dot xy. Oh, actually, this also works, by the way. This is also something you can do. It's really cool. So if you want to switch the RGB values, you can do something like that. That's honestly pretty cool. You can do xy divided by higher resolution xy. That does the same thing. Oops. And this might work. No. Okay. You can have that in then. And let's see if that works. Yeah. So did you see that this is okay? This is not okay. And you might be like, wait, what is the difference? So integers are actually not, not good. Almost everything you do in shaders is floating point. And so if you want to divide a floating point number by an integer, it actually doesn't allow it. And so when I tried dividing these numbers by 10, it will not compile. But if you divide by 10.0 or 10 point for short, then it works. And you can see the image actually changed quite a bit over here. Zoom in, enhance, right? Zoom out. So this is tiling 10 times as much. So we'll tile it twice. 1, 2, 1, 2. See that? So these are the kinds of things you can do. Reject int to return to float. Exactly. Embrace monkey. So so it's really cool. Like and like I said, when you go through the tutorial, you'll kind of learn this. It's like C, but it's got like these little features in it that are actually kind of nice. It's actually kind of fun to play with, and you kind of like, honestly, I kind of miss it when I work in C++ and I'm doing stuff like this. I'm like, I just want to be able to divide by 5, and have it apply to all 3 elements. So this is how you grab a pixel out of a texture. So here's your texture. Texture is just a 2D image. And we're going to grab from I channel 0, that's this guy. We're going to grab X, Y. X is, these are basically UV coordinates. And we're going to go, it goes from 0 to 1, and we're grabbing that pixel. Static color, I channel 1. So this is static. Looks like this, or this. And so we are grabbing a pixel from the rock image here. We're grabbing a pixel from the static image here. And then we are going to take the sign of the times. Frequency is set to 1. If we up that 10, it's now flashing 10 times faster. That's going to hurt my eyes. Let's go back there. So time times frequency times vector 4. So vector 4 is RGBA. A is transparency, which is almost always 1, which means fully opaque. So we're going to grab the texture color. That's R. If I change that X to an R, exactly the same, right? If I change it to like a G, though, it will probably be a little bit different. Maybe not. I don't know. Yeah. So it's going to grab the red value and multiply it by the from how far left. Oh, yeah, from how far left to right it is, and then if you have a mouse click, it's going to take the mouse click. If you're not clicking is 0, so it doesn't do anything. So if you mouse click, you can see how it's like doing the color shifting here. So it's grabbing the mouse location divided by the resolution, which is again going to give me a value from 0. Over here, it's not doing anything, right? If I click on the very left side, it doesn't do anything. To 1, if I go to the right side. And then for the second channel, the green channel, it's grabbing the green value from here, multiplying by the how far down we are. And so that's why you see these like rainbow patterns as it goes left or right. And then for the red, green, blue value, it grabs the blue value and multiplies by static color.r, which is this. So it's adding in a little bit of static in the red channel only, and then it's fully opaque. And then that's it. That's the whole thing. So that overall RGBA value gets multiplied by the sign of time. And so that will fade to black, and then it'll go negative. Oh, no, we got an absolute value on there, so it bounces back up. Without that absolute value, we're going to get negative color. That's black. Then it comes up, and then when it goes to negative, we get nothing. For half the cycle, we get black as the color. So that's why I slapped an absolute value on there. So when the sign goes negative, it goes positive again. And instead, we can do this. So this is grabbing the texture and multiplying it by static. So where static is white, white is 1, 1, 1. It does nothing. Where static is black, 0, 0, 0, you're multiplying by 0, 0, 0, and you get black pixels. So this is a way of blending together two different textures, adding static essentially on top of the picture. So an even simpler fragment would be like this. And this is just displaying the texture. So all my shader is doing now essentially is grabbing the value of the texture at this location and then returning that color as the result. And so this is a very simple texture map shader now. Nothing else matters in it because all I'm doing is this line of code here and then returning the texture. Okay, that is it for today, guys. Thanks for coming out, and I'll see you guys in a week. Peace.